Okay, folks, getting into our next learning goal on diffusion, activation controlled reactions in solution. And I know we've predominantly spent a lot of time looking at gas phase chemistry in this class, but we can take what we learned from the gas phase chemistry and apply it to how things might differ in a solution. So when we think about what will happen as things react in solution, they've got to diffuse through all of these solvent molecules, where we'll define diffusion as the tendency of molecules to move from an area of high concentration to an area of low concentration. So in this area here where they are absent of A's and B's, A and B will diffuse into that place where there's a void of molecules so that they can fill in that space. So they will approach each other with rate constant Kd. And as they get close to each other, they are supported by this solvent cage. So I'll call this AB thing an encounter pair. Okay. And additionally, A and B could also diffuse away from each other depending on the concentration gradients. So that's why we can see that there is an equilibrium describing this process. However, if the solvent cage has held them together long enough and they've had an effective collision, then that encounter pair can go on to form products. So if we were to balance this whole mechanism, right, it looks like just a very simple A plus B goes on to make products occurring at some second order rate constant that I'll write K Rxn. And then of course we could write dP by dt as K Rxn times A times B for this overall process. But now what we need to consider is what is the rate of diffusion compared to the rate of activation. So that's really what that Ka stands for. Okay, so let's look at that in the next slide, and we're going to apply the steady state approximation to do this. So for the mechanism, we'll write dP by dt. So that only depends on this bottom rate right there. So we'll write that as Ka times my encounter pair, which I'll denote as A dot 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 B. So as we might guess, this encounter pair is some type of a transition state, right? And then I could write my dAB by dt as the following. So that's produced in the forward rate describing diffusion, where an A has to diffuse to find a B. It is also described by then the negative rate, so the reverse reaction in that equilibrium, which is Kd prime times A dot 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 B. And then, of course, it disappears again in the final reaction as minus Ka times A dot dot B. And then we're going to apply the steady state approximation to this situation by setting that all equal to 0. And what we want to solve for here is the concentration of our encounter pair so that we can plug it back into our rate of product formation. So now if we do the algebra here, I'm just going to present that directly. We end up with the following. So that becomes Kd times A times B all over Kd prime plus Kc. Okay? And if we plug that into our dP by dt, we get the following. So that's going to be Ka times all of that. So we'll have Ka times Kd times A times B. And I'm going to keep the rate constants over here, and hopefully we will see why in a minute. So then that's divided by Kd prime plus Kc. And so now if we think about this, this looks very similar to the expression that we came up that describes A plus B going on to form products with rate constant KRxn. So the product and sum of all of these rate constants gives us our apparent overall rate constant. And now the game that we need to play is what happens if diffusion is in control, or what happens if activation is in control. So let's rewrite that. dP by dt equals Ka. I probably should have had the reaction written up on this slide again. Kd prime plus Ka. Okay. And then now that's all times A and all times B. So if we have the following situation, so if Kd prime is much, much less than Ka, and let's get those reactions written again. So A plus B forms our encounter pair AB, and that occurs with forward rate Kd and reverse rate Kd prime. And B, our encounter pair, goes on to form product with rate constant Ka. So what we're saying here is if this reverse step is very slow in comparison to the step that goes on to make products, then we can say the following. So when we're looking at this now, if Kd is much, much less than Ka, then we can cancel the Kd prime from this expression, and we're left with the following. dP by dt equals, so we're ignoring Kd prime because we assume it's small in this limiting case. And then the Ka and the Ka cancel, and what we're left with is Kd times A times B. So Kd equals the overall rate of the reaction, and this is what we would call a diffusion limited reaction. Okay, diffusion limited. So in other words, the rate limiting step is how long an A takes to diffuse to a B, and then once that happens, the reaction goes very quickly. So what about the other hand? So what if Ka is much, much less than Kd prime? So now just kind of looking, just focusing in on this relationship here, if we ignore Ka, then what we're left with now is the overall rate constant of the reaction equals the following. That's Ka times Kd over Kd prime. So that's forward rate constant over reverse rate constant, which is equivalent to the equilibrium constant. So this is always true in the case of a simple activation-controlled reaction. So in other words, in this activation-controlled reaction, if we kind of zoom in at the top of our activation energy, right, our encounter pair is sitting right there, AB. I'll write the double dagger right there. And so now what this indicates here is Kd prime, being much, much faster than Ka, we're limited by this encounter pair being able to turn over and go to products. So it is an activation-controlled reaction. Okay. All right, and then we'll pick each one of those apart individually in the next videos. I'll see you then.